Hey everyone, let's get started. Welcome back to CS 2040S. I hope that everyone is now done with their midterms after the last couple weeks of busy midterms and ready for the rest of the semester. Exciting rest of the semester ahead. Hope everyone enjoyed the CS 2040 midterm. I don't want to talk too much about it today since there are still two people who were sick and still have to take it. So I don't want to say too much about it today, but it looks like it was a good challenge, which is great. And in particular, if you found it hard, my advice would be to look at it and see what you can learn from it. We actually spent a lot of time putting together the midterm, trying to choose the questions carefully so that they would well test the material, so that they would be fair, and most importantly, so that you could learn something from it. Since that really is the goal of this whole exercise anyways. So to the extent that you found it hard, that's great. You should see what you can see what positive you can take away from that, what you can learn from it. Okay, again, I'm not going to say any more about the midterm right now though. Okay, good. Let's, what else is happening the second half of the semester? As you might have seen, there is a new competition up, an optional competition up. The Speed Demon competition. This is your one chance this semester to show how fast your code can be. Okay, so it's a simple data processing task. There is a special leaderboard for it, so you can compete and write the fastest code that you can. I see someone has a comment in the chat saying the Speed Demon site is not working now. Well, if not, we will get it back up and running. It was working earlier, it looked like. Okay, so that's one thing going on right now. The other thing that's going on, you might have noticed, is there's a new problem set out. I'm sure everyone's excited by. And this is a fun problem set because you get to produce your own special automatic writing program. Okay, is again a relatively simple sort of automatic writing technique where you can produce all sorts of fun and interesting texts with it. So this picture here, by the way, is actually of I think 19th century automaton that could that could actually write out letters by hand with this quill pen, every so often dipping its pen in the ink. I think this is the one I actually saw when I was in Neuchâtel a couple of years ago. It's really an amazing automaton. Go watch a video of it. They're entirely done with clockwork. Okay, anyways, alas, you won't be building an automaton. You will instead be writing a program, but hopefully it will be fun. Okay, great. So that's what is happening on that front. In terms of content in this class, we have a little bit more to talk about with respect to hashing. Okay, so today we're going to finish up talking about hashing, and then we will start talking about graphs next week. Okay. So just to remind you, since this was now long ago in the past, pre-midterm days, we were talking about hashing. What is a hash function? We talked about how to resolve collisions using chaining and open addressing. Okay. We talked a little bit about how to deal with Java, and then we had just begun to talk about table resizing, and that's what I want to talk about today is table resizing and maybe a little bit about sets if we have time to do that. Okay. And then we'll be done with hashing and get to move on to graphs next week. Okay, so let's remember where we were. We are talking about abstract data types. Sorry, we're talking about symbol tables, an example of an abstract data type. A symbol table is something that lets you insert key value pairs, search, delete, and so on. Okay. We talked about hashing as the solution for implementing a symbol table. Where you are hashing a small set of keys from a big universe into a set of buckets. Okay. The key problem you run into with hashing is collisions, in that you might have two keys that collide. They're mapped to the same bucket. This is unavoidable. And we talked about two solutions to this: chaining and open addressing. Okay. The question that we were talking about at the end of last class was how big your table should be. And we were saying that, okay, if we're using chaining and if we have simple uniform hashing, we know that the optimal size of our table is somewhere around theta n, right? That's basically the right size for your table. If your table is too small, there'll be too many collisions. If it's too big, there's too much wasted space. So you want it to be about the same size as n. Since we don't know n in advance, we're going to have to figure this out adaptively by growing and shrinking the table. So you start out with a small table, some fixed size, m equals 10. When the table gets too full, you're going to increase the size. And when it gets too small, you're going to decrease the size. Okay. And we talked about the cost of that. In general, the cost of changing the size of your hash table looks something like this. It's linear in the size of the old table, the size of the new table, and the number of elements you have to copy. Okay, great. We went through a few different ways you might increase the table size. You might try increasing your table size by 1 every time, and that led to quadratic cost, order n squared cost. We then said, okay, that's obviously too slow. Let's increase our table size a little bit faster. At every step, we can double our table size. Okay, that's a little better. Now, every time we increase our table size, it's going to again cost order n. Okay, and so the total cost of all the resizing we have to do is going to be order n now. Okay, that's nice. And so in general, that means that the average cost of an insertion is going to be about order 1, right? We insert n items into our table. That's fine. The cost of all the insertions is going to be order 1 per item on average. The cost of the resizing is going to be order n total. And so that means that the total cost of everything is about order n, average cost order 1. That's pretty good. That's what we wanted. Okay, great. We then said, great, squaring is better. Doubling the table size is better. What if we grow even faster? What if we square the table size? There's some interesting cases where squaring is actually better, but not in this case. So in this case in particular, if you square your table size every time, it means when you grow your table, you're going to be spending n squared on growing it. Okay, so now the cost of your resizing is order n squared for inserting n elements. The average cost of each insert is now n. This is too fast. You should not grow your table this fast. This doesn't work. Okay, and so where we were at the end of last class, where we stopped was saying this is the best rule we have so far for growing our table size. Whenever the table is full, if n equals m, then what we should do is we should double our table size, set m equal to 2m. Every time we do this, it's going to cost something like order n cost, and that's fine. We can afford every so often to do this. Every so often we spend some time doubling our table size, copying everything over, and moving on. Okay, great. So the next thing to think about is what happens when we delete items from our table. Okay, so we know how to delete things in general, right? You calculate the hash, you find the linked list it's in, you iterate through the linked list till you find the item, you delete it, you're done. And in general, the expected cost is going to be order 1 plus n over m, the same as the expected cost for inserting. Okay. So once again, as long as our table size is roughly theta n, this will be an order 1 cost operation. Okay, great. So let's think about then what rule we should use. So last time we noticed that the right rule was doubling. So let's do the same thing, right? So now if our table is full, if n equals m, we're going to double our table size. And if n is smaller, we want to half our table size. Actually, even before we look at this, let me put up a question on Archipelago for you, and you can think about whether.
Yeah, okay. Oh.
Hello, does someone have a question? Okay, I'm muting everyone because I heard some crosstalk there. But if you have a question, raise your hand, let me know. So this is what you're seeing on the slide, of course, is one version of a rule you might use to shrink. The question I have an Archipelago actually gives you 6 different options, I think, for possible rules. So why don't you go look at that and tell me which of these rules you think is best. I'd like you to think for a sec about what happens, what are the dynamics of this type of rule? What happens with this type of rule? And this is also the usual good excuse to go over to Archipelago and see how the lag is doing today. But it's worth thinking about for a sec. It's an interesting question. It's not obvious. Okay, everyone's had a few minutes to think about it, so let's go on and see what happens. Let us try out this first thing here that I suggested. So the first thing I suggested here was that if n is equal to m, then we're doubling the table. And if n is less than m over 2, so once your table is half empty, then we divide your table size by 2. Okay, let's start out with that. Okay. And let's see what happens. So here's the rule. Let's look at an example. So here's an example. You start out with your n equals 100, m equals 200, right? This is sort of a nice initial state. We start deleting things from our table. We delete down to 99, okay? And so now we shrink to m equals 100, right? Because our table is now half empty, so it's clearly time to shrink. Okay, so far so good. Now we insert something into our table. We insert one more item into our table. Our table size now gets up to n equals 100. Okay. Oh no, our table is now full, n is equal to m. Let's double our table size and go back up to m equals 200. Okay, so we see the basic operation of these rules, right? Anyone see a problem yet? Let's go on. So let's continue with this execution. We start with n equals 100, m equals 200. We deleted 1. And so we shrunk our table by a half, right? This is the rule. If our table is half empty, we shrink by a factor of 2. And so now we have this 99 and 200, and we spent a cost of 100 doing this, roughly, order 100, okay? I see a question in the chat saying, why did we shrink so much? Well, we're shrinking by a factor of 2. We're just dividing the table size by 2 because the table is half empty, okay? Now we insert an item. Our table is now full, n equals 100, m equals 100. So we grow by a factor of 2. And again, we spend roughly 100, order 100 cost growing our table. And I think now hopefully the problem is clear. We go ahead and we delete 1. And now we spend 100 shrinking our table. And we insert 1 and spend 100 growing our table. And we delete and we insert and we delete and we insert. And every single operation, we're going to have to update the size of the table. This is terrible, right? This is basically having to grow or shrink your table on every single operation. I see a question in the chat saying, what's the cost of deletion? So the cost of deletion here, the cost of deletion itself is roughly order 1. The actual cost of the deletion, where this cost of 100 is coming from, is the cost of resizing the table. And the cost of resizing the table is proportional to the size of the table. I chose 100 here as sort of something that's around n equals 100. That's sort of the right proportionality constant. I didn't want to get into worrying about the exact constants. But basically, every operation, we have to pay something like theta n cost to double or shrink the array. Okay, great. I'm sorry, I see a question. If you shrink, it does not follow the load factor. So the point is, I think that what the question in the chat is getting at is that this is clearly not the right thing to do, right? This is not a very good strategy for growing and shrinking. We are clearly doing something wrong because it is too expensive, okay? So let's try something a little bit different, okay? So here is another option. So in this case, if n is equal to m, then again, we double. But now we're going to be a little bit lazier about shrinking our table, right? So we're not going to shrink when n is less than m over 2. We're only going to shrink when n is less than m over 4. Okay, so we're now going to wait till our table is 3/4 empty before we waste our time shrinking the table. And then again, if the table is 3/4 empty, we're going to divide it in half. Okay, so you'll notice in this case, we are leaving a gap. We have a factor of 4 here and a factor of 2 here. And this gap between the 2 and the 4 is going to make things better. Okay, but I claim this is not obvious. Is this right? And how do we decide whether this works? You really have to go through a bunch of cases to try to decide if it works. But I claim that the way you can tell this works is the following. Every time you double your table of size m, then there must have been at least m over 2 new items that have been added since the last time you doubled or shrank the array. Okay. And similarly, every time you shrink your table of size m, there must have been at least m over 4 items that were added or deleted since the last time you doubled or shrank your array. Okay, so the key point is there have to have been a lot of operations since the last time you did a double or shrink, right? That was the problem we had here, was that there was only one operation and then we had another double or shrink. Here I'm claiming that can't happen. I'm claiming there have to be a lot of operations to force you to do another double or shrink. Okay, so let me just try to give you a little picture to see and sort of intuitively what's going on. Imagine you start over here with some operation that doubles the array from your table from size 10 to 20. There were 10 items in your table initially. Now there are 20 items in your table. Sorry, there were 10 items in your table initially. Now your table is of size 20. You have enough space. And so some more insertions start happening. Okay, maybe there are sort of 5 more insertions that are happening. At least 5 insertions are happening. In fact, there have to be 10 insertions here before your table of size 20 gets full. When your table of size 20 gets full, then you're going to double again. Okay, there are now 20 items in your table. You double your table to size 40. Okay, now your table is size 40. Well, how many deletes have to happen before you're going to shrink? Well, you have 20 items in the table. The table is size 40. Luckily, we only are going to shrink if the table goes down to a quarter full. That is, when the table only has 10 items in it, then we're going to shrink. This is where the extra gap is helping us. Now, there certainly have to be at least 10 deletes in this space here. That's great. So we can shrink our table down. Our table is now size 10. We shrink it to 20. Okay, fine. Now we go back and do some more insertions. Notice that 10 more insertions is now going to cause us to have 20 items and double the table size. Okay, so this is just sort of an example of what's going on. One subtle point you might notice, you might look at, why did I choose these m over 2 and m over 4 factors? So the m over 4 factor at least seems like it's right for this one here, right? The table grows to size 40. There are 10 deletes. We have to shrink again. Okay, but you might look at this m over 2 and say, wait a sec, that only means there have to be 5 inserts. Why did you choose m over 2? Why didn't you choose m? In this particular case, in fact, we know there have to have been 10 inserts. But if you look more carefully at this case here, in this case, m over 2 is 10. So if the insert was immediately after a delete, then this case turns out to matter. As I said, this is a little bit more subtle than it might appear at first glance. Okay, but without going through a careful formal proof, hopefully this has at least convinced you that this overall claim is true. When we double a table, there have to have been roughly m over 2 new items added. When we shrink a table, there must have been at least m over 4 items deleted. Okay, great. So all of this, as I said, is a little more subtle than it looks. So you might ask for a more careful set of techniques for keeping track of all of this, right? You might want some better tools to keep track of these costs. And that's what amortized analysis is. And I'm only going to spend a few minutes on amortized analysis. We're not going to go through it in great detail. But I'd like to at least give you an idea of what it means. So when you get to 3230, you will say, aha, yes, I have a basic idea of why amortized analysis is interesting and important. And then you'll see more details in 3230. Okay. But basically, the point of amortized analysis is to give some techniques for capturing this idea of average cost. Okay. And the analogy that most people give is something like, say, paying rent. Right? We don't usually worry about paying rent every day. Maybe you pay $900 a month in rent. You could think of this as $30 a day. It's useful to be able to think of it in both ways. Okay, these sort of average cost. Okay, so fine. Here's the actual sort of formal definition of amortized cost. We say that an operation has an amortized cost T of n if for every integer k, the cost of k operations is less than or equal to k times T of n. So this looks a lot like an average cost, right? Or at least it implies something about average cost, right? If the total cost is less than or equal to k times T of n, then certainly the average cost is going to be less than or equal to T of n. Okay, but be careful because it's not exactly the same as average cost because it says it's true for every integer k. At any time you look at it, it happens to, the average cost is less than or equal to this cost. So let's look at an example. So here I'm going to claim this sequence of insert operations would have an amortized cost of 7. Why is that? Let's look at all the possible times we might look at. 5 is less than 7. Good. 5 plus 5, 10. 10 is less than 2 times 7. Good. 15 is less than 21. Okay. 5 plus 5 plus 5 plus 13. Okay, that's going to be less than 28. Excellent. And then if we add 7 again, we are still less than 35, less than or equal to 35. Okay, in fact, we're exactly 35. So at every single step along the way, the average cost is less than or equal to 7. So we can say that the amortized cost of this operation is at most 7. Okay, but amortized is not average. I have just taken these set of operations, 5, 5, 5, 13, 7, and shuffled them into a different order. So they are 13. The 13 operation comes first. And now the amortized cost is not 7 anymore. Why is that? Because you had to spend 13 right there at the beginning at step 1. If you stopped right then, you would spend more than the accepted average cost. You would spend more than 7. No good at all. The amortized cost is not 7 for this sequence of operations. Okay? So when we say that the amortized cost is at most something, we are saying that whenever you stop to look at things, that's going to be the average cost. Okay? Yeah, this is just going through that some more. So in the example of hash tables, that's what we were just looking at. If we want to say the amortized cost is good, we want to say that if we look at a sequence of insert operations, whenever we stop, we have still paid at most order 1 per operation, even if we had to spend a bunch of time doing some resizing. Okay, so this is important that we better start with an empty table, right? If we start with a table that's full and the very first operation is a resize operation, that's going to have a bad amortized cost. Okay, if we start with an empty table, which is what we tend to talk about, then everything should be good, right? By the time we've inserted k elements, for any k you look at, we'll have spent order k cost. Okay, so the insert operation has amortized cost order 1. Okay, this was just some slides on more slides on amortized analysis and the banking method. Let's sort of skip this for here. Okay, let me give you another example of sort of another common classic example of amortized analysis, another sort of simple example. Let's think about a binary counter. Okay, so a counter abstract data type. It has 2 operations, increment and read. Okay, this is just a log n bit counter. It counts up to n. Life is good. I can increment and get a 1. I can increment and get a 2. I can increment and get a 3. Binary counter, excellent. So here's a question. So here's a question. What is the worst case cost of incrementing this counter? What is the most expensive? If the counter has a maximum value of n, what is the most expensive this can be? I will give everyone another 10 seconds to input something on Archipelago, and then I'm going to go on. 3, 2, 1, onwards. The cost here is log n. There are log n bits in our counter, and in the worst case, all of those log n bits have to flip, right? So in particular, here's an example where we are doing an increment. We have log n minus 1 bits. We do a single increment, and it spends cost log n. And of course, it takes log n bits to count to n, right? Okay, so if I asked you what is the cost of this increment, in the worst case, the answer is order log n. Okay, great. But we can do a more careful amortized analysis. And the sort of key interesting observation is that when you do an increment, only 1 bit changes from 0 to 1, right? There's only this 1 bit over here that actually changes from a 0 to a 1. Everything else is changing from a 1 to a 0. So that's interesting. Okay. So let's see if we can use that. There are many bits that are going to change from a 1 to a 0. But for them to change from a 1 to a 0, they have to have been previously turned into a 1. Everything started out at 0. At some point in the past, this bit changed to a 1, and then now it's changing back to a 0. So you can think of this as we can pay for the fact that the bit is changing from a 1 to a 0 by the fact that it previously changed from a 0 to a 1. Okay, so let's see how this goes. One way to think about this is in terms of some sort of bank account. This is the accounting method. Whenever you are changing the bit from a 0 to a 1, you can imagine you're adding a $1 to each of these little bank accounts. And then whenever you change it from a 1 to a 0, you're paying with that dollar. So the total cost is going to be 2, 1 for increasing it from 0 to 1, 1 for decreasing it from 1 to 0. Okay. Here, this was a picture with all the little bank accounts underneath it. I increase it from 0 to 1, I add $1 to that little bank account. I do another increment. I pay this dollar here to decrease this from 1 to 0. At the same time, I increase this from 0 to 1, and I pay an extra dollar in doing so, and so on. And you can keep going with this example. So each increment is going to add $1 to change something from a 0 to a 1, and it's going to spend a bunch of money to turn things from 1s into 0s. Okay. Finally, you get to the end here. You've done a whole bunch of increments. We've now accumulated all of this saved up money. We've been saving to pay our rent all month, you can imagine. And now I do this expensive increment operation. I'm going to spend all of this saved up resource to turn all these 1s into 0s, and then I'll just spend $1 new. I'll add $1 new to the system here. Okay. So hopefully this gives you a way of looking at this idea of amortized analysis, a way of looking at this idea that the amortized cost of an increment is 2. Okay. For every operation, we do 1 unit worth of work to actually change a 0 to a 1. We add $1 to spend in the future to change this back from a 1 to a 0. That's our 2. And then everything else that we do is going to be paid for from the bank account. Okay. So the amortized cost of an increment is 2. And if you think about this a little more, you'll realize what that means is that after every operation, the amortized cost you'll spend, the average cost you'll spend after every single step is going to be 2 times the number of operations you've done. Okay, good. So as I said, this is just sort of the very quick sort of overview of amortized analysis. We're not going through this in careful detail. You'll see more in 3230, but now you have some sense of what we mean when we say the amortized cost is something. Okay, and so in the case of hash tables, what this means is once we've established this fact that when we double a table of size m, there were m over 2 add operations that came first. These previous m over 2 add operations you can think of as adding money. This resizing is going to spend money. Same thing on delete. These m over 4 previous delete operations are adding money, are saving up money. This operation of size m is spending money. There's a question about repeating the part about the amortized cost being 2 again. Let me, instead of going back to talk about the counter some more, let me talk about this in the context of a hash table, okay, which is where I really want to get to anyways. Because that's, I think, the counter is just another example. But the hash table is what we're really talking about in this class. So for the perspective of the hash table, you can imagine that every table has a bank account. Every time an element is added to the table, we're going to add some money to that bank account. We're going to save up some money for later. Okay. Whenever we resize the table, we're going to spend some of that money. We're going to spend some of our, again, think of this as saving for the rent. Every day you put $30 aside in your bank account. At the end of the month, you have your $900 to pay rent. Okay. Same thing. Every day you're going to save up some work to do. Okay. Every day you're going to save up some order 1 work that you can do later. You're going to do a little bit of extra work now to save it up for later. And then when you need to do the resizing, you'll have enough saved up. Okay. So here we go. In the case of a hash table, resizing a table of size m takes order m time. So whenever the resize operation happens, we have to have saved at least order m time, order m resources to do that resize. Okay. So if we resize a table of size m, then we know that at least m over 2 new elements have been added since the last resize. If each of those elements added order $1 to our bank account, we now know that we have theta m dollars saved up, excuse me, and that's enough to actually pay for this order m resize. Okay, great. And the same thing holds for delete. Okay. Another way of thinking about this, There's a question, does this bank account have anything to do with cash? No, there's nothing to do with cash here, unless that was a joke, in which case, haha, funny joke. Okay, so so to think about this, say the same thing a slightly different way. You have our hash table. We're inserting k elements into the hash table. As we insert those elements, we're sort of saving up, we're deferring order k dollars that we're going to use later to pay for the resizing. We're going to spend order k dollars to actually do the insertions themselves. And so the total cost is order k. Okay. And that means that we always have enough in our bank account to do the resizing. Okay. Good. Okay, so hopefully, what I'm hoping this gets across is connecting this back to what we actually want to be saying. We want to be saying that after each insert operation, the time we've spent up to that point, after any k insert operations or insert and delete operations, the total that we have spent up until that point, including all the insertions and resizing, is at most order k, right? That's what we're trying to show. And this deferred versus immediate is a technique for showing that. It's an analytic technique, for a bookkeeping technique to help keep track of how much time we've spent in order to show that. But the thing that you want to make sure you really do understand is how to see that after k operations, we've only spent order k time. That's the important fact in the end. Okay. Okay, good. So the conclusion to come to is that for a hash table with resizing then, let's say, for example, a hash table with chaining, and say we're assuming the simple uniform hashing assumption. Okay. Well, then the cost for insertion, we already know the expected cost for each insert operation is order 1, right? Searches don't require doubling or shrinking the table. The search has expected cost order 1, and that's because of the simple uniform hashing assumption. Okay. The insert operations, by contrast, insert operations, well, we're not doing any extra searching on inserts. We're not worrying about duplicates for our inserts, right? No searches here. So there's no hashing relevant, no hashing assumption you need for inserts, because you just inserted at the beginning of the linked list. But there is this fact you have to pay for doubling and shrinking, and so we have an amortized cost of order 1. And now, of course, if we got into combining randomized things with amortized things, then it's even harder to talk about. And so I don't want to worry about that. That's why I've separated out the insertions here, which have no randomization. They're just amortized. And the searches here, which are just randomized, but not amortized. Okay, great. Okay, good. So that's I think about all I want to say about table resizing and doubling. So that's we finished talking about table resizing. In the last 20 minutes I have, I'll talk for a couple minutes about a variation of a hash table, which is a set. Okay. So this is so previously we were talking about a symbol table. Symbol tables let you insert key value pairs and so on. Sometimes, though, you don't actually need a key value pair. Sometimes what you are trying to maintain is a set of stuff, a collection of stuff. It's not a key value pair. You just have a set of stuff you want to maintain, whether something is in or not in the set. Okay. Much like a hash table, we're not defining any ordering on our items, right? These are unordered items. But in this case, speed is critical. We want to get an answer as quickly as possible to whether something's in our set. And space is critical. We want to maintain this in the minimum amount of space. Okay, great. And in Java, by the way, a hash set implements something like this interface. So what's an example of where you would want to set? Imagine that you have some list of friends on Facebook, perhaps. Maybe you have a lot of friends on Facebook. People do these days. Some of your friends are online at any given time. Some are offline at any given time. You want a data structure that's going to keep track of which of your friends right now are online or offline. Okay, so you can imagine you're maintaining a set of online or offline friends. Just a set, no key value pairs, just a set of things. Another example is a spam filter. You have a collection of good email addresses, a collection of bad email addresses. You want to quickly be able to decide when you get a new email, is this in the set of good email addresses or the set of bad email addresses? Okay, great. So this is our abstract data type, a set data type. Okay. we can solve this problem right now and not waste any more time on this by saying, okay, let's just use a hash table, right? We can just use a hash table to implement our set. For each item that we have, we just hash it to wherever it goes, add it to our table, and we are done, right? We could stop right now. But I claim this doesn't actually completely solve the problem that we want to solve. In particular, I claim we can do better in one of these dimensions. Oh, wait a sec. Did I turn on the wrong question? I turned on the wrong question here. Let's try again. Where's the question I wanted to ask? Okay, here we go. It should now be open on Archipelago. Which problem does a hash table not solve among these questions? Fast insertion, fast deletion, fast lookup, small space. Okay, so if you think about this for a second, what you'll realize is it doesn't actually solve the space problem at all. In fact, the hash table is going to take up more space than just storing a simple list of items, right? So in fact, it's going to be worse than sort of a simple naive list. I mean, it's okay, you can search it faster, so that's good, but we haven't really saved any space. So the question to ask is, if we only want to maintain a set of things, we don't need a perfect exact list, we just want a set of things, no key value pairs, can we do it faster than a hash table? Or sorry, can we do it with less space than a hash table? Less space. So space is the key issue we're going to be focusing on. And why does a hash table take so much space? The issue is that you have to actually store the keys and stuff like that in the hash table. So if I want to hash this stuff into my table, I actually have to store, say, gmail.com in my hash table, right? And why do I have to actually store the keys in my hash table? Well, I have to store the keys in my hash table so that we can resolve collisions, right? If I don't store gmail.com in my hash table for the thing that I'm hashing, then I can't tell if there's a collision or not. Okay. So, okay. There's a question in the chat about what if you use an AVL tree? And yes, there are things you do with an AVL tree too. But an AVL tree with hashing, the hash tables might have similar problems. You're still going to need all that space to store the keys. The AVL tree, if you need to store the keys in the AVL tree, it's going to take however much space you need to store all the keys. Okay. So let's see if we can do this using less space. And we're going to call this a fingerprint hash table. And the idea of the fingerprint hash table is we're not going to store the keys in the hash table. The only thing we're going to store in our hash table is a 0 or a 1 for every element in the table. Okay, so an m-bit table, so an m-size table is only going to take m bits. Okay, and so that's easy enough, right? This is just a table of bits. So this is why it's called a fingerprint, is you can think of this sequence of zeros and ones as a fingerprint for the set of items that you want to store. Okay, the algorithm becomes simple enough, right? There's nothing complicated you have to do. It's almost the simplest way you can imagine storing stuff. When you want to insert a key, you simply hash the key and then set that table bit to 1. Okay. If I want to look it up, what do? I hash the key, I look it up. If there's a 1 in the slot, I say, yes, your item is in the set. That's it. That's all I'm going to do. Okay. So the key difference then between a fingerprint hash table and a regular hash table is what? Okay, we don't have a lot of time, so I'm not going to actually spend time waiting for Archipelago on this. But what is going on with Archipelago? Oh, I don't know what's going on with Archipelago. Sorry. Anyways, let's not spend time on Archipelago right now. The key point here is that the fingerprint hash table is not going to prevent collisions, right? But it does not store the key in the table. Okay, same sort of hash functions, right? Same time to calculate hash functions, and I hope you understand how it's different. But the key point is we're not storing the key in the table. Okay. Fine. So then you might ask, what happens if there is a collision? If there is a collision, tough luck. We're not going to worry about it. If there's a collision, then there's still going to be a 1 in the slot, so be it. That's the way it is. Okay. So let's think about what happens then. On an insertion operation, there's no problem, right? I want to insert these two things into my table. I insert them both here. I put a 1 in the slot. Everything works just fine. Okay. On the other hand, let's think about a lookup operation, right? Let's say I'm looking up Microsoft.com. This is a set of URLs. If the URL is actually in my set, web cache, I just need my set here, it's always going to return true, right? Even if there was a collision, if there was some other thing that also hashed to the same slot, it does not matter. If this thing was in the set, then I set the bit to 1, then I'm going to find it on a search operation. So this is no false negatives is what this is called, right? If it's there, it always returns true. Okay. But on the other hand, let's see what happens if we look up an item that is not in the set. Okay. If we look up an item not in the set, it may sometimes report true, right? So there are false positives. Sometimes a positive answer, it says yes, is not correct. A false positive, right? So in this case, we inserted Microsoft.com. We looked up rugby.com. Rugby.com was never inserted into our set. It just happens to hash to the same bit. Oh, well, we will get an incorrect answer in that case. So the sacrifice here is we are going to save space, but in return, we are going to occasionally get incorrect answers. But the incorrect answers will only be false positives. They will not be false negatives. Okay. So for example, and again, I don't want to spend time on Archipelago, but you can think about these examples. If you are Facebook and implementing something to keep track of the set of online users, you might want to think about which way is better. Would you prefer to have false positives or false negatives? Would you prefer to believe that Fred is online when he is not? Or would you prefer to believe that Fred is offline when he is not? Okay. And if you use a fingerprint hash table to do this, what's going to happen? You're going to sometimes believe Fred is online when he is not. Fred is going to collide with another user who is online. So when you look up Fred in your fingerprint hash table, it'll say, yes, Fred is online, even though he is not. Okay. And you can go through a similar example for email addresses. Okay. This one I claim is subjective. It depends which you prefer. Okay, so I'm not going to go through the mathematical analysis. Again, we just have a couple minutes, but just to give you a feel for what's going on, the probability of false negative is 0. Like I said, there are no false negatives. You can calculate the probability of a false positive. If you work it out, it ends up being, 1 second. Is the slide not advancing for some reason? Okay, well, I hope it's working. Let me know if it's not working correctly. So you can analyze the probability of a false positive, and you discover it's about 1 over e to the n over m. Okay. So the probability of false positive at most 1 minus 1 over e to the n over m, if you assume the simple uniform hashing assumption. Okay. And so if you then do some algebra, work it out, what you'll discover is that if you want to have a certain probability of false positives, say you want a 5% probability of false positives, then you need to have the table be sufficiently big. In this example, you need m to be at least 13.5 times n if you want to only have a 5% rate of false positives. Okay, or I think, here we go. I have a picture if you want to see this. So you get to choose your rate, choose the rate of false positives you're happy with, and then that will imply the table size you have to choose in order to get that rate of false positives. Okay, and so then you have to compare this table size to the number of bits you would need for a regular hash table and see if you are doing better or not. Okay, so what we've seen then is fingerprint hash tables are nice because they don't store the keys. They only store this 0, 1 vector. That makes them smaller. On the other hand, there's a trade-off. They only use one bit per slot, but you might need a bigger table in order to avoid collisions. Okay, great. Okay, can you do better? That's an interesting question. One idea for doing better is called a Bloom filter. In a Bloom filter, you don't just use one hash function, maybe you use two hash functions. So you hash each item to two different slots in the array and set them both to 1. Okay, so in this case, here's my insert function. I take two different hashes. Can't draw on the screen anymore. Okay, I take two different hashes, hash 1 and hash 2. This identifies two different bits from my array, and I set them both to 1. Now, when I want to do a search, when I want to do a query, I check both of those two bits, and if they're both 1, I return true. If either of them is 0, I return false. And what you can tell is this is going to reduce the number of false positives, right? It's going to reduce the chance that I collide in both places with someone else. Okay, so it can still have false positives, but it will be smaller. It still has no false negatives, just like a fingerprint hash table, but in general, we'll use a little bit less space. Okay. And there's this sort of trade-off. It feels like each item takes more space in the table. You actually need 2 bits per item, but now it requires 2 collisions for a false positive. Okay. Again, I'm skipping the analysis because we don't need to cover that today, but you can go through the analysis. On the slides, I'm assuming a bogus incorrect fact of independence. Just remember that if you're looking at the slides later. But what you will discover is that in this case, you end up with an expression that looks something like this. Okay, so in particular, if you want a 5% false positive rate, now you need n over m to be something like this 1/2 log 1 over 1 minus square root of p. And if you work it out, you end up with m at least 7.9 times n. Okay, great. What I mean by independent is in the analysis here, we're assuming that things are independent. Let me not get into that right now. I can talk about that, the analysis later if you want separately. So here is, again, what the graph looks like now for the false positive rate versus the table size. And if you can remember what the curve looked like last time, this curve is lower. But wait a sec, I'll show you both curves on the same chart in a second. If you think 1 hash function is good, 2 hash functions is better, what about k hash functions? Has to be even better, right? So you can generalize and use many hash functions. In this case, you get a slightly better probability, a slightly reduced probability of false positives. And so this is what the set of curves looks like. If you only have a fingerprint hash table, that's this blue line on top. K equals 2 gets you a little bit better. K equals 4 a little bit better. K equals 8 a little bit better. More hash functions gives you a smaller table for the same false positive rate. Okay. Great. So you might say, let's optimize. What is the best choice of k? It turns out there is a best choice of k. You can solve for that. If you set, for example, m equals 10n, if this is the maximum amount of space you want to use, in this case, you would discover that you need about 6 or 7 hash functions to get the best Bloom filter. So this is something that actually, so while it looks like I'm showing you a bunch of math, because I'm going through those slides quickly, it turns out Bloom filters are quite useful in practice. It turns out that Bloom filters, and this is for 18N. It turns out that Bloom filters turn out to be a quite useful way in practice of getting very small data structures for maintaining sets. Okay. Good. So what's the moral of the story? The moral of the story here is that fingerprint, if you want to maintain a set of stuff and you're able to tolerate some amount of error, some amount of false positives, then a fingerprint hash table is often a great way of saving space. A Bloom filter is an even better way of saving space. And as I said, over the last couple of years, the last 5 or 10 years, I think we've seen more and more use of Bloom filters because they're a pretty powerful way to store stuff in an efficient way. Okay. I think that's all I'm going to say about this today. There are a couple of other issues you might think about in terms of Bloom filters that we haven't gotten into at all. Things like how you deal with deleting items from a Bloom filter. You better do it carefully. What about other sorts of operations on your Bloom filter, like intersection and union? It's great. You can actually implement those type of set operations quite efficiently using these type of fingerprint or Bloom filter systems. Also great for distributed systems. I want to send stuff over a network. Better to keep the amount of stuff I want to send small. Anyway, so Bloom filters turn out to be quite useful. Okay, good. I think that's all I'm going to say today then. We are out of time. This is the end of the hashing segment of the class. Hopefully by now you know what is a hash function. You know how to resolve collisions with chaining and open addressing. You know how to implement hashing in Java. Well, that's what you're doing on problem sets these couple weeks. We talked about table resizing, and we talked about sets. So that is all for today. We will stop there, and I will see you all next week. Thank you. So I'm happy to go back over the math. I don't think, I mean, extra time, not really, it's about 5. So this is, but I'm happy to go back over the, math if people are interested. And I'll leave it on the slides to look at later if you want. Oops, sorry. All right, one thing at a time. There's a question about the math for fingerprint tables. So let me go to that first, and then I can address the other question that's here. Okay, so I want to say, what is the probability of a false positive? Okay, and this is for the fingerprint table with one hash function. Let's start out with that. So let's say I have a table of size m, and there are n elements in it, and I want to say, what's the probability that there's going to be of no false positive? Well, there is a 1 over m probability that you will collide with something. So there is a 1 minus 1 over m probability that you will not collide with that item. And there are n different items you might collide with. So this 1 minus 1 over m to the n is the probability you don't collide with anything. Okay. And then using our favorite standard approximation, 1 minus 1 over m to the n is about 1 over e to the n over m. Okay. So this is the probability you don't collide with anything. And so another way of looking at that is you're basically saying, here I have this item. I want to know what's the probability that no other thing hashed to the same slot, right? There are n other things that might have hashed to this slot. What's the probability that one of them did hash to this slot? Okay, and so that's where you get that this probability of a false positive is at most 1 minus 1 over e to the n over m. Okay, does that help with give you some sense of what the analysis is doing here? I'm trying to remember who asked the question about this. Okay, and then if you for the Bloom filter version, you have to look at multiple hash functions. So you have the exact same calculation for each hash function, right? This is the same calculation as before for the chance that you hit something, the chance you don't hit it, the chance you don't hit any of them. There are now 2n possible things because each thing is hashed twice. Okay, but now you have to have 2 collisions, and that's why this ends up being squared. But this is what I mean about independence. Squaring it here is actually implicitly assuming that they're independent, but of course they're not, because the fact there was something there means there's more likely to be something elsewhere. Anyway, so these technical details and doing this math actually correctly ends up being quite tricky and can't quite fit on a slide nicely. Isn't the size of the hash table essentially halved? I mean, you could think of it that way. You basically it feels like you need a bigger hash table because each item takes more space in the table. So it feels like you need more space in the table, but now you can actually make the table smaller because you're less likely to have a collision. So you have these 2 competing forces, right? 1, to make the table bigger so that you have space for both hashes. 2, make the table smaller because you can tolerate, because it's harder to have a collision. It turns out that in general, or at first at least, the second term dominates. The fact that you need 2 collisions is squaring the probability, while this is only changing it by a factor of 2. Eventually, as you start increasing k, eventually this more space ends up taking over, and that's why you end up with a curve that looks like this, where at first you're getting a huge amount of benefit as you increase k from like 1 to 2 to 3 to 4. You're getting a lot of benefit because you are really decreasing your probability of error because you're squaring, cubing, raising it to the 4th power, and so on. But then eventually you start needing to put too much stuff in your table. This is for a fixed size table. Eventually, you start filling up your table, and the fact that you are increasingly adding stuff to your table starts dominating, and then you run out of space. I don't know if that helps, at least to the intuition of what's going on here. Isn't the probability of collisions doubled? We are taking that into account in the analysis. That's why there's a 2n up here. Right? The fact that this 2n is in fact exactly doubling the fact that each item you might hit in 2 different places. Okay, so that's where that 2 shows up, or k will show up in the k version. But then you square it, which turns out to be more important. Okay. Yeah, so as I said, I skipped the math intentionally because it's a little beyond what, it takes a little more time to go through a little more carefully than I have here. So, you know, but if you spend a little time thinking about it, I think you can, I'll leave the slides for this and you can think about it. And I'm happy to talk about it more later. I think it's doable. It's assuming you're not worried about this independence problem, it's not too hard. If you actually want to do it right, it's tricky. There was also a question about deleting, I think, earlier in this chat somewhere. I don't know if that person's still around. The issue with deleting is, as the person pointed out, if you delete items, that can cause trouble. And so people propose things like a counting Bloom filter, where you're actually going to store a small counter instead of 1 bit so you can delete. On insert, you'll increment. On delete, you'll decrement. As long as the number of collisions is small, you only need a couple of bits for this. In practice, people often have 2 or 3 bits per element in their hash table in order to handle deletes. And that turns out to almost always be good enough. How do we expand a fingerprint hash table, and doesn't using a fingerprint hash table mean that we're unable to expand the hash table? It's going to be harder to double and shrink because there's no obvious way to go and rehash everything. I think that's correct. In general, fingerprint hash table works well when you have a reasonable estimate for the amount of stuff that you want. You have a reasonable estimate for your set size, and so you know that's what you have. Now, of course, you can imagine doing something like you have your fingerprint hash table, it's gotten full. You create a new one of twice the size, but you keep the old one. Now you just query both of them, and this will only increase your lookup cost a little bit, but it's not ideal for obvious reasons. Other questions on this? Other questions people want me to talk about? I feel like there were more questions up in the chat, but I've lost them by now. So if you are, which was Wayne's question?
Hey, Prof, do you remember the question I asked last week about double hashing and the uniform hashing assumption?
I forgot to go look that up. I'm sorry. I promised I'd look that up, and I forgot what with the midterm and stuff. I will still have to go look that up for you. I'm sorry.
I'll ask you again next week. Thanks, Prof.
Yes, ask me again next week. Good. Thank you. Yeah, sorry. So Ryan says that you're curious about Wayne's question. Which Wayne's question do you mean here? Oh, the one just now. Okay, good. Let's see. What else is here? Does using or instead of and for lookup increase the number of false negatives, decrease the number of false positives? So I think what you're saying is that what you're asking here is, in this case, I was saying that you only return true if both items are 1, not if either item is 1. Well, as long as you're going to set both items to true on an insert, then you might as well in some sense, right? If when I do an insert, I set both items to 1, they really should both be 1, right? I really should only return true if both are set to 1. Now, you might be thinking about what happens with deletes. What happens if there's a if there's a small counter that underflows, and now on delete, only one of these is set to 1. But if you're worried about that case, you're not going to get any benefit from the Bloom filter. If you're returning true, if either of these is 1, then really the Bloom filter isn't helping you all that much. I guess it's helping on deletes then. Maybe if you're optimizing for deletes. But somehow that doesn't seem like that's the useful case. Okay, one sec. I'm going through the questions here in order. What about hash functions with locality? What about hash functions with locality? I'm not sure what to say about hash functions with locality. Can you clarify what you're asking? Is there a difference in runtime between a fingerprint hash table and a regular hash table? I mean, the hash function, calculating the hash function is about the same. The lookup, it depends. If you're worried about chasing linked lists, it might be a little bit faster. Looking at a fingerprint hash table is only 1 bit to look at, so you don't have to worry about chaining or anything. So I suppose technically lookup could be a little faster. But in practice, if your collision resolution is good, if you don't have long linked lists or you don't have lots of open addressing pointers to chase, then it probably won't be too different. But yeah, fingerprint hash table and a Bloom filter should be a little faster in general than a regular hash table. Since the fingerprint is smaller, I feel like we could set an absurdly large table with no real cost to doing so. Depends what you mean by absurdly large table. I mean, the advantage of a fingerprint hash table is saving space, right? So to the extent that it's so absurdly large that it's the same size as a regular hash table, you might as well use a regular hash table and not have to worry about this problem of collisions and false positives. If by absurdly large you mean you can make it, 7 or 8 times n, then yes, that's often why it's useful. I see the question about the amortized analysis on the counter. I'll go back to that in a sec once we're done with the hashing questions here. Does the hash function used here have to satisfy uniform hashing assumption? In this case, the simple uniform hashing assumption. You better assume that your hash function is giving you some sort of random distribution over the buckets, right? If your hash function is very bad and maps everything to one bucket, there'll be a lot of collisions. Things won't work very well. When we resize the hash table, how do we change the hash function? So the problem with resizing the hash table here is there's no easy way to go and figure out where things belong, right? You no longer have the set of keys in order to rehash them into a new hash table. So I think this is a question that came up earlier. When you're using a Bloom filter, you often want to have a good estimate on the number of items you have in advance so that you don't have to be constantly resizing. Because again, resizing is hard without the set of keys that you need to rehash. Without knowing what's in your set, it's hard to rehash. It's like a fingerprint. It's easy to go from a person to a fingerprint. It's hard to go from a fingerprint to a person. Same type of thing. Given a set of keys, it's easy to produce the fingerprint table. But given a fingerprint table, it's very hard to produce the set of keys. Okay. With a high enough K, can we store the entirety of the information of the content in the table? If you're storing the entire content in the table, you might as well just use a hash table. There's no benefit you're getting from the Bloom filter at that point. The benefit of a Bloom filter is the fact that you're trading off this false positive rate for less space. K becomes a bitwise representation of the input. Yes, so again, in some sense, if you make your table big enough and you increase K enough, eventually you're storing all the same information. But once you're doing that, then you're not getting any benefit anymore. Even with a long thing, it only works for 64 elements. I'm not sure what that refers to. Okay, and something about deleting in Bloom filters. There are a variety of ways people deal with deleting in Bloom filters. The simplest way is what's called a counting Bloom filter, but there's certainly been a bunch of work on how to optimize deletions. As I said, Bloom filters have been a very active area of research over the last couple of years because they've just turned out to be so useful in practice. So there's been a whole bunch of work on this. Feels like there will be a lot of clutter by the end. Not sure. Garbage collection with Bloom filters. Not sure you can do garbage collection. Again, same problem. You don't know what's really gone away. You don't really know what the keys are. Okay. Does the Java implementation of hash set also run into the issue of false positives for lookups? I don't remember how hash set is implemented, honestly. I'd have to go look at the Java implementation of it. To the extent that it's just implementing a hash table, then it's just implementing a hash table. And it might well be that's what it's doing. Does this count as a form of data compression? I don't know, maybe. Depends what you mean by data compression. If it is, it's lossy data compression. It's literally a fingerprint. Yes, exactly. Okay, let me go back to the question earlier on the counter. There was a question about this counter that I've been postponing for a while. So what exactly was the issue here what exactly is the question I should answer? So the point here is that we're only going to, when we do an increment on our counter, there's only going to be one item that changes from a 0 to a 1, right? There's only this one thing that changes from 0 to 1. Everything else are ones changing to zeros. Okay. And so from a amortized analysis accounting perspective, what we'd like to think about is only actually counting the cost for the 0 to 1 change and paying for the 1 to 0 changes using accumulated money from our bank account. Okay, and hopefully the intuition here of these bank accounts makes some sense. That if every time we do an operation, every time we do an increment, we spend one unit of time doing the 0 to 1, and then we just spend 1 unit of time doing nothing. We're saving it up in our bank account for later. We're basically deferring that unit of work till later, but we're going to count it as 2. We're going to pretend that we've spent 2 units of time, even though we've only spent 1 unit of time, okay? Because we've saved up a unit of work later. And the idea is that after we've done a whole bunch of these increments, we have a whole bunch of deferred work that we've already accounted for, but that we haven't actually spent real time on. And that gives us enough time to actually spend on the rest of the increments. But I'm trying to remember who asked the question. If the person who asked the question is still around, if you'd like to clarify what's confusing you, I might be able to address it better. No? What would be the amortized cost in the 13 example? I think it would be 13 if I remember the example you are saying correctly. You were talking about this example here, right? So in this case, the amortized cost I think is 13 in the sense that the first one is less than 13. The second one is less than 2 times 13. This is less than 3 times 13. This is less than 4 times 13. This is less than 5 times 13. So the amortized cost here is 13. Basically, at every unit of, and again, you can think of it as saving up work. Here, the amortized cost is 13. I actually spent my whole 13. Here, the amortized cost is 13. I'm going to pretend that I've done 26 units of work, even though I've only done 18. And I'm going to imagine saving the remaining 7 units of work for something later. And again, here I've really only done 23 units of work, but I am accounting for 39 units of work, with the difference of it being saved up later. How important is amortized cost for 2040S? I don't know. This is a question I don't answer. My default answer to the question of is X important? My answer is yes. Of course it is. If I didn't think it mattered, I wouldn't have spent time talking about it. But obviously, some things are more relevant than others. In that case, wouldn't the amortized cost change drastically depending on the input? It might. So in general, that's right. In some cases, the amortized cost might depend on the input, in which case you want the worst case. You're saying for the worst possible input, what is the amortized cost? This is worst case analysis, right? So if it is possibly the case that your first insert has cost 13, then tough luck. I mean, that's just what it's going to be. It also means, though, that when you talk about amortized cost, you often need to say something about the initial state of the system or something like that. So for example, the amortized cost of an insert in starting with an empty hash table will be different than the amortized cost if you start with a full hash table. If I start with a completely full hash table where the first operation is going to double, well, tough luck. Okay. But you're right that you have to be a little careful when you talk about amortized analysis as to what precisely you are talking about. We take the minimum cost for all steps, for all iterations, for all steps. Yes, exactly. It's sort of the minimum average cost if you look at every single unit of time. Sorry, minimum. It's like the average, not the minimum, the maximum average cost if you look at every single unit of time. It's basically another way of talking about average, but a sort of more powerful notion of average. A notion of average that guarantees you that at every given time you're always bounded by that average, right? You're not going to suddenly be much worse than your average and hopefully plan to catch up in the future. You have to get ahead before you can spend that time. Does that make sense? A little bit? Any other questions? Is there an average cost? So sure, you can also, you can also talk about average cost. That's also a reasonable metric. Often we prefer amortized cost because it gives you a guarantee at every point of time. Again, theorists tend to like this sort of worst case analysis. In fact, in practice, people like this as well because they know that at any given time, things won't be too bad. But certainly you can talk about average cost as well. And average cost is, yeah. But if you talk about worst case average cost at all units of time, do you end up with amortized? You end up with something very like amortized cost, right? So if you're talking about average cost, you need to say average cost over what? Average cost over n operations, sure, you can talk about that. If it's average cost for every single unit of time, well, then that's essentially amortized. Other questions? Okay, if there are no other questions, then we will call it a day. So have a good weekend and see you all on Tuesday.